In this video, we're going to be going over exponential limits and evaluation. So number one is that exponential limits are going to be continuous everywhere, which is going to allow you to do direct substitution. Secondly, we have that these negative exponents are going to decay. So e to the power of negative infinity is equal to 0. Thirdly is if you have positive exponents, that is going to explode. So e to the power of infinity goes to infinity. Fourth is exponentials are going to dominate in growth over polynomials. So e to the power of x is going to be greater than x to the power of 5 when x is going to infinity. So if you have the ratio of x to the power of 5 over e to the power of x, that is going to be going towards 0. And we have these famous exponential limits that you should memorize, which is number one, limit of x approaching 0 for e to the power of x minus 1 divided by x is equal to 1. And limit x approaches 0 for a to the power of x minus 1 divided by x is equal to natural log of a. Next, if you have limit of x approaches infinity, 1 plus 1 over x to the power of x, that's equal to e, Euler's number. Now let's do some examples. So first, if we have limit of x approaches to 0, e to the power of 5x minus e to the power of 2x, all divided by x, we can substitute in 0, and we have 1 minus 1 over 0 is equal to 0 over 0. Now, this is an indeterminate form. So what we can do is we can rewrite this. We have instead 1 plus 5x plus something minus 1 plus 2x plus something, all divided by x. So this is going to simplify down to 3x plus, continuing on with the pattern, over x, and then this is going to be 3. The reason why this is right is because when x is near 0, right, e to the power of kx is approximately 1 plus k times x. So let's do another example. What if we have the limit of x approaches 0 for e to the power of 3x minus 1 minus 3x? So we are going to use expansion here, which means we can say e to the power of 3x is equal to 1 plus 3x plus 3x squared, all over 2, plus continuing on. And that's the same thing as 1 plus 3x plus 9x squared over 2, plus continuing on, we have 1 plus 3x plus 9x squared all over 2 minus 1 minus 3x all over x squared. So this is equal to 9x squared divided by 2 plus continuing over x squared. So that x squared is canceling out. We just get 9 over 2. So constant and linear terms cancel, so x squared is going to control our limit. Third, we have the limit of x approaches 0 for e to the power of x squared minus 1, all divided by x squared. So we're going to let u equal to x squared, so we can do u substitution. So as x approaches 0, u is going to approach 0. So that means that e to the power of x squared minus 1 all over x squared is equal to e to the power of u minus 1 all over u. So this is going to equal to 1. This is matching our standard limit, which is limit of u approaches 0 is for the function e to the power of u minus 1 over u is equal to 1. So that matches. Let's say we have the limit of x approaches 0 for e to the power of 2 to the x minus 1, e to the power of 5x minus 1. So both the top and the bottom, they're going to go to 0. Now, for standard limit behavior, this is going to be approximately 2x, and this is going to be approximately 5x. So we get 2x over 5x, which is going to be 2 over 5. So again, near 0, e to the power of kx minus 1 is going to behave like kx. So for our next example, let's say we have limit of x approaches infinity for e to the power of 2x plus 3 times e to the power of x, all divided by 5 times e to the power of 2x minus 7 times e to the power of x plus 1. So we're going to factor the exponential. We get e to the power of 2x times 1 plus 3 times e to the negative x, all divided by e to the power of 2x times 5 minus 7 e to the power of negative x plus e minus 2x. Now, you can cancel out common terms. We can be left with 1 plus 3 e to the power of negative x. And down here, we just have 5 minus 7e negative x plus e to the negative 2x. So we can see that as x approaches positive infinity, we have e to the negative x approaching 0, and we get 1 plus 0 over 5 minus 0 plus 0 is equal to 1 over 5. So e to the power of 2x is going to dominate, and e is going to dominate e to the power of x, and also its constants in this problem. So for our next example, we have limit of x approaches infinity. We have 4e 3 to the x minus e to the power of x plus x to the power of 5, all divided by 2 times e to the power of 3x plus 9 x to the power of 7. So on the top, we have this as our dominant term, and on the bottom, we have this. So we're going to take the ratio of the two, 4e, 3x. We have 2e power of 3x. That's going to be simplified to just 2. So our answer is going to be 2. Let's say, for our next example, we have limit as x approaches infinity for x to the power of 3 e to the power of negative 2x. Rewriting this, we have x cubed e to the power of negative 2x is equal to x cubed e to the power of 2x. So our exponential growth is going to dominate polynomial growth, which means that this is going to go to 0 because you have this really large number on the bottom, and then this is going to be smaller on the top. So you keep dividing by a large number, that's going to converge to 0. Now, let's say we have limit of x approaches negative infinity for x to the power 4 e to the power of x. So as x goes to negative infinity, we can see that this e to the x part is going to go to 0. However, this part is going to go to infinity. So if we rewrite this using let u equal to negative x, we can say that if x is going to negative infinity, then we have u is going to go to, negative infinity. U is going to go to infinity. So that means that x power 4 e to the power of x is equal to u to the power of 4 times e to the power of negative u. And if you rewrite that using a negative fraction, because you have a negative exponent, so you just flip that e to the denominator, you have e to the power of 4 and u to the power of 4 in the numerator. So we have that the exponent dominates the polynomial, right? So then if we know e to the power of 4 goes to 0, we now have this in a form where we know that this whole thing is going to go to 0. So exponential decay is always going to beat your polynomial growth. For our next example, let's say we have the limit of x approaches 0 for e to the power of 4x minus e to the power of negative 2x, all divided by sine x. So let's use some expansions. E to the power of 4x is equal to 1 plus 4x plus, continuing on, we have e to the power of negative 2x is equal to 1 minus 2x plus, continuing on. We have e to the power of 4x minus e to the negative 2x. That's approximately going to be 1 plus 4x, using our expanded forms, minus 1 minus 2x, which is going to equal to 6x. And we know that sine x is eventually going to be similar to x. That means that e to the power of 4x minus e to the power of negative 2x all over sine of x is going to be approximately 6x over x, where that x cancels out and we just get 6. So for our last example, let's say we have limit of x approaches to 0, e to the power of x minus 1 minus x, divided by 1 minus cosine of x. So if we use our expansions, e to the power of x is equal to 1 plus x squared all over 2 plus, continuing on, and also e to the power of x minus 1 minus x is equal to x squared over 2 plus, continuing on. 1 minus cosine of x is approximately going to be x squared over 2. So then all of this, we can rewrite this as an approximation where this will be x squared over 2 over x squared over 2. So that's just the same number over itself, making all of this equal to 1. So the numerator and denominator are going to vanish to second order. So this is 1.